So I apologize in advance for going very fast through some slides, but I will be happy to share the slide deck with you all afterwards. So very quickly, CHIME is today I'm focusing on CHIME, the Copernicus Hyperspectral Imaging Mission for the Environment. It's a mission which is part of the Copernicus program, for which ESA is basically the implementation actor and for the European Commission, and CHIME in particular within the Copernicus ecosystem provides data, provides spaceborne measurements and subsequent products to stimulate the uptake from end users. The Copernicus services, for sure, our core, say, operational producers of data for the European Commission, but also much larger number of scientific and operational users who feed and are part of what we call the downstream economy of which is enabled by the Copernicus data, free and open for all sorts of use, as you know from the last years, most likely. CHIME is part of the 6 Sentinel expansion missions that you have here. In particular, it's focused on some, let's say, critical application domains and the exploration and exploitation of raw materials is one of them. So that's why we are talking about CHIME today. In principle, the CHIME mission objective is to provide routine hyperspectral measurements at global scale over all land and coastal areas, and it's targeted to support, in particular, European and global policies for the monitoring and management of natural resources and food security. So there are 2 primary application domains for which the mission has been designed, which is agriculture on one end, so vegetation, crops, and soil monitoring, and the other one is raw materials, so basically minerals. Let's go. There are a number of secondary applications which will be enabled by the availability of CHIME data, but these are not what, let's say, we're not driving the mission design. So what is the mission design? In principle, in the key specifications are that CHIME will be a carpet mapping mission, so a la Sentinel-2, so to speak, not tasking, but carpet mapping of all land and coastal areas, quasi-nadir observation, I mean the nadir pointing with a relatively small SWAT, field of view, up to 84 degrees sun zenith angle, covering the full spectral range linear to sphere 400 to 2500, with a spectral sampling of 8.4 and a full width of maximum, so spectral resolution of about 10 nanometers. All this at 30 meters spatial resolution, which with 2 satellites, which is the final constellation, brings basically an 11 days geometric revisit, with, of course, a slightly better coverage time at latitudes higher than the equator, basically, due to partial orbit overlap. We ensure that this is done with a very high radiometric accuracy, high SNR, and a very low spectral and spatial misregistration in order to enable basically full spectrum retrievals as much as possible. So the user data products which will be produced routinely are top of atmosphere radiance and reflectances and bottom of atmosphere atmospherically corrected surface reflectance. We are planning to, we're building our processor in order to be able to generate these layers, the surface reflectance layers, both in the original sensor geometry to avoid any spatial mixing, and in auto-rectified geometry, basically, with associated uncertainties. And just going very fast, these are the prototype products that we are currently developing in order to demonstrate some of the potential of the mission. This is not meant to be operational products. It's not in the mandate of ESA at the moment to provide any operational product beyond surface reflectance. Okay, but in order to prototype, to show what we can do, we are developing some retrievals, and there is also something related to geology application and minerals. However, I must admit that there is much more to do on that, based on heritage and on let's say future development. And I'll show you some examples based on missions which are already flying, imaging spectrometers which are already flying. Here an example from NMAP, from DLR, launched in 22, and it's just an example of a site in Chile, where basically they managed to map the alteration minerals, and I think this is white mica specifically, and the position of the minimum of the absorption of white mica in order to identify aluminum rich and aluminum poor areas. Basically, of course, we are limited to the very surface. Remote sensing and optical remote sensing cannot solve each and every problem, but whenever there is exposed rocks, basically, and soil for other applications, we can definitely do something. Here, just another example from our colleagues at JPL, with which we are constantly working of the applications of the tetracorder algorithm to an emit image. Emit is another imaging spectrometer on the ISS, and through the combination of a large number of observations from it, actually, our colleagues at JPL have been able to prototype and to demonstrate, let's say, the first regional maps from an imaging spectrometer with real data, and you can find much more details in the publications and online from our colleagues. But very short, sorry, I didn't check what time I started, but I will just go quickly through the other slides. In principle, the space segment is going very well for CHIME. So the contract, actually, we're now in the CDR of the entire system. So the critical design review, it means that after in a few months, basically the full design of the entire satellite and instrument will be completely fixed. There is not much wiggle room, to be honest, already now, but this is because we are performing very well vis-a-vis the requirements so far. So we are actually on a very good track. It's just for your information, let's say, a view of how the instrument is assembled, and the 3 spectrometers, which basically build up the unique 130 kilometers watt, unique, of course, for an imaging spectrometer so far. And this gives us basically the capacity of doing the carpet mapping and every 11 days with 2 satellites. This is just for fun. If you want, you can have a look at one of our latest tests, where a model of the full instrument has been tested for all sorts of vibrations. I want to highlight that we have we are, in order to prepare for CHIME, we have developed a full end-to-end simulator where we generate scenes, or synthetic scenes from in the performance, in the scene generator module, and then we replicate, we propagate the top of atmosphere, we replicate the observation, we can test basically our level 1 processing, level 2 processing, and then check the performance versus the inputs of all these process. And one of the inputs of all this process can also be campaign data, which I want to point you to because they are available. We have had several campaigns, particularly a large one in 2021, where a number of sites have been imaged with an airborne sensor, but also by Prisma, another imaging spectrometer from the Italian Space Agency. And this data set is available. If you are interested, just let me know. And we have incredible exchange with our international partners in order to build basically a common ground for global imaging spectroscopy. This is a golden era for us. With the community has been waiting for these imaging spectrometers to become a reality for many decades, and And recently we gathered this community at ESTEC in November for the third of a series of international workshop on international cooperation of spaceport imaging spectroscopy. I leave you these links if you want any further information on CHIME, and thank you very much for your attention and your time today.